Today I want to talk about some recent results on the incompressible Euler equation. And I'm going to try to speak in sort of elementary way about as much as I can. So let's first recall the Euler equation in dimensions 2 and higher. So it models the motion of a divergence-free velocity field. And so we're going to be considering this on R3. And usually you supply it with an initial value, which we call U0. Okay, so well-known fact about the Euler equation is conservation of energy. And on the other hand, you also have some local well-posedness results. So these are pretty old results. So you have dating back to the 1920s. You have the following results. So if U0 is given in C1 alpha of R3. So okay, the classical results were on bounded domains, but in fact I think maybe they had some industrial applications in mind, but you can easily extend it to R3 as long as you're careful about conditions at infinity, which I'm not going to talk much about. But basically you just need that the gradient of the velocity belongs to some LP space. Okay. Okay, so if U0 is in C1 alpha, there exists a time, a positive time, and a unique solution, U, which is C1 alpha in space and time, up to time t. Okay, so this is a classical result. And coupled to this result, you have blow-up criteria. So the blow-up criteria is that it ceases to be in C1 alpha at T star if and only if the limit as T goes to T star of the L infinity norm of the curl is plus infinity. So this, for this type of equation, for hyperbolic equations, or the gradient, the full gradient of U is usually used to control the smoothness. So you need, because of the divergence-free condition, you only need the curl of U. Okay. And this is a well-known criterion due to Beal, Kato, and Maida. And corollary of this is if U0 is in C infinity, then there's a unique C infinity solution until possibly this happens. Okay, so until something like that happens. Okay, and so today I want to discuss a recent result which is the following. So So theorem. So there exists an alpha which is positive. It's a small number, and U0 in C1 alpha on R3 intersect L2 of R3, so that the unique local solution, so the unique local solution U in C1 alpha up to time 1 satisfies this blow-up. So satisfies that the limit as t approaches 1 of this integral is infinity. Okay, so what it shows is that the classical theory can't be made into a global one. Okay, even though that's possible in 2 dimensions because this quantity is conserved in 2 dimensions. But of course it doesn't answer the smooth question, right? I'm not making any claims about that. So the method of proof, so the proof will be based on constructing an exact, so an exact, I don't mean by have a formula or anything like that, but an exact self-similar blow-up solution for the Euler equation. So that's okay. So let me forgot to introduce an important quantity which is already on the board. So we call omega the curl of the velocity. So so you construct an exact self-similar blow-up solution of the form omega of x and t is 1 over 1 minus t times some profile x over 1 minus t to the lambda. And then you prove that it's stable with respect to certain kind of perturbations, which allows you to have compactly supported vorticity. So that's first you construct the self-similar profile, and then you prove stability of the profile of the blow-up. And the second part is joined with Nader-Masmoudi and Tajgoud. So many of the ideas which go into the stability are already used in the construction. So today I'm just going to talk about the construction of the profile.
You said the stability lets you make it compactly supported?
Yes. Yeah. The vorticity. So
Vorticity.
yeah, the velocity being compactly supported doesn't make all that sense anyway. Even if it's compactly supported, at some time it won't remain, but the the vorticity is. Okay. Are there any questions about statements or anything like that? Okay, so now I want to discuss the proof. So the proof is based on a few different ideas. But more or less the key idea, so the key idea is to try to isolate simple uh, uh, a simple model of 3D Euler with a stable blow-up, and so that the Euler equation can be written as a perturbation of this model. So ideally, I'd like to be able to write the Euler equation as something like this, where this problem you have a nice blow-up solution. Maybe you can even write it down explicitly, and then you discuss how that gives you a blow-up for the full problem. Okay, so passing from a blow-up for something like this to a blow-up for the full problem is where you use modulation. But that's one key element. Another key element is how you can actually write the Euler equation in this way. So how do you even find what n1 should be? Because you could write the Euler equation like this, trivially, but exactly how do you do it in a way that works? Okay, so first, to start out, I think I just want to begin with an example of how the modulation works. So this is a very simple example, and but to understand what's going on, it's important to have a few examples in mind. So let's maybe just think that suppose that, let's just suppose you could write the Euler equation in this kind of form. So you cannot, but let's say that you could. Epsilon is a small parameter. N is a quadratic nonlinearity, which scales like f. Okay, so okay, I can't write over here, but in my mind, I'm thinking about the vorticity equation, right? So you're thinking that you have this equation, and of course the growth of vorticity, so this is just a transport, and the growth of vorticity is coming from this term. Okay, so what you'd like to do is think about the f squared sort of represents that vorticity stretching term. Okay, so now let's proceed. Suppose that I could prove a blow-up on this equation. So I know how to do that. So in fact, there's an exact similar blow-up. So when epsilon is 0, then, so let me solve this in 1D. So for x greater than or equal to 0 and t greater than or equal to 0, then you have a solution. So you have f of x and t is 1 over 1 minus t, f star x over 1 minus t is an exact solution when f star is 1 over 1 plus x. Okay, so what am I saying? So you have this kind of picture. So if you just take the Riccati equation and you take this data 1 over 1 plus x, okay, normally we think of blow-up as this single point that goes to infinity, right? But actually the blow-up is it's exactly self-similar. So this point goes up, but there's also a concentration. Okay, so you have, this is the calculation you can just check. Okay, and now you ask, if I have this perturbed problem, can I get a perturbed self-similar blow-up? Okay, so that's what you'd like to do. So if you do this very naively, you'll fail. Right? So if you do this without taking into account that putting a perturbation should change the speed of blow up, should change the time of blow up, right? So you shouldn't just say, okay, I'm going to say that for this problem, the blow up will be this plus epsilon. Okay, it's not going to work like that. So let's relax what we search for. So we search when epsilon is positive. We try to search for a solution of the form okay, so we allow, and this is the modulation, right? So this you're allowing for a different scaling in x, and this one you could have done a slightly different thing, but I'm allowing the blow-up time to change. Okay, so this will give us basically two free parameters to help us solve the problem. Okay, so then if you plug this in to this equation, what do you get? So you get 1 plus mu times f plus, let me call this variable inside z, 1 plus mu times 1 plus lambda z dz equals f epsilon squared plus epsilon n of f epsilon. Okay, so that's, I just plugged into this equation my ansatz. Okay, and if you differentiate in time, you get these extra terms.
What did you assume about n, the scalar of n? It's linear n?
I assume that it's quadratic and has the scaling of f squared. So u dot gradient omega scales like omega squared, right? So that's the kind of, right. Any question? Yeah, so that's important. So n is quadratic and has the scaling of f squared.
What does the second statement mean? Besides the first one, say quadratic.
But like this thing, dx minus 1 f times f doesn't have the scaling of f squared, right? Because scaling means if you see what I mean? So this scales like minus 1, right? If you compose this with lambda, you don't get lambda x, you don't get f of lambda x of this thing. You see what I mean? So n of f of lambda x should be the same as n of f of lambda x. That's what I want. That's what I mean by the scaling of f squared. And quadratic is quadratic like homogeneity on the outside. Okay. Okay. So like the transport term in the vorticity equation. So u dot gradient omega, right? The omega gives you plus 1 and the Biot-Savart law gives you minus 1. Right? Because u is one derivative better than omega. Okay. So all right, so now any other question? So now you say, okay, I want to write f epsilon as f plus g. Now g is going to be small, so you want to find g, lambda, and mu, all of order epsilon, so that this equation can be solved. Okay. All right. It takes a moment to get used to these many boards. So, Okay, so so what do you get when you plug this ansatz in? Well, the main thing is you get the linearization around f of this guy, and the linearization of this around mu equal lambda equals 0. Okay, so you get L of g is equal to like minus mu f minus mu plus lambda plus mu lambda okay, so this maybe f epsilon plus g squared plus n of f epsilon. Okay. So f, and you get wait, I'm confused. Maybe it's f epsilon.
N should be evaluated probably at F, because it has an epsilon.
Yeah.
Oh, okay.
Yeah. Yeah. The main thing is this guy. Understand what this guy is, right?
Wait,
So-
I'm a bit confused here. You really mean fx sub epsilon in these terms?
yeah. So some terms I don't really care if it's f plus g, right? Because it would be the. That's okay. We can really make sure. So you take this term and you throw it over there, and you take the purely mu terms and you throw it over there, and the
So what happened to the term epsilon squared? There is no epsilon g. That's what I'm worried about.
say that again.
Epsilon fg is not the
That's L. So L is right. So L of G is G plus Z dzg minus 2 over 1 plus Z G, because this is F. That's 2F. Yeah. So I have to put that in because that's important. Right? So you get this. And now, normally how you think about it is that you're going to invert L and solve for G iteratively. Right? So if L was invertible, you do that. But there's another problem that you want N to include transport terms, possibly. Okay, so if N includes transport terms, then there's derivatives on the right side, so you shouldn't do it that way. Okay, so how you should solve it is if you could prove that L of G inner product with G in some space X, whatever it is bigger than a constant G in the space squared. So it's coercivity of L. So if you could prove this, so if this, and you also knew that N of G inner product with G in X is less than C G in X squared plus maybe G in X cubed, right? Something like that. Then you could, by compactness, not by compactness, you could get an a priori estimate on G, right? What you would get is an equation of this form. You get something like G in the space X squared is bounded by, so you have some non-homogeneous terms, so maybe you'll have like epsilon, so let's allow for constants, epsilon gx plus gx cubed, something like that. Okay, that's coming from this term. Okay, and then this should tell you, as long as you do it in the correct way, that G is of order epsilon. Okay, does that make sense for everybody? That's the kind of thing. So we have to. So the main thing is to get something like this. So this is the key to having like a stable self-similar blow-up. Okay. So in this case, X is not just going to be L2. So it's a small fact, so you just have to think about it a little bit. So a small fact. So fact, yes.
Just I'm still a little confused the way you wrote the equation.
Yeah.
Why did you write mu f minus mu plus lambda f? I mean, what's the point?
Oh, sorry.
There must be something missing.
Yeah, sorry. This is z dz. It doesn't, yes. It doesn't make a big difference exactly what this is, but you're right. Yeah. Thank you. Sorry. Okay, so how do you prove? So let's think about this operator. It's g plus z dzg minus 2 over 1 plus z g. Okay, so this has a small problem that when z is very large, right, this term is not there, right? So you're talking about this term which is positive in L2, right? So if you take inner product of this with g just in L2, you get positive. But then if you think z is basically 0, then the whole thing looks like it's negative in L2. Okay, so one thing people use is to put weights. So it turns out that if you put a weight, maybe even an equality, if you use the weight so if you just put a weight, you work in the right space, suddenly it becomes a positive operator now. Okay? Okay, and this weight, yeah.
This weight is going to force you to make g 0 at 0.
Exactly. So this weight forces you to make g at 0 to be 0 and g prime at 0 to be 0, right? For anything to work. And that is why you have mu and lambda. So mu and lambda are the modulation parameters, and they're used to guide the solution into the coercive part of L. Okay, that's all that's happening in this. And this is okay. This is as a method is being used on a number of problems, and the more parameters you have, the more you can do, I guess. So. Okay, but are there any questions about this general frame? It's very elementary, but this is the general technique. Okay, so now we want to figure out how do you write the Euler equation in that way. Okay, so now the question is, how do we write the Euler equation as... Okay, so let me write what it is. Okay, now this is what I call the fundamental model. Okay, so it's very similar to the Riccati equation, but it has some non-locality. So this L12 is some non-local operator, which I'll talk about in a little bit. Okay, and so how do we do this? So the one place we're drawing inspiration from, there's kind of two places. So drawing inspiration from two sources. First, it's a work of Constantine, Lax, and Maida. So they essentially wrote down like some simple model of 3D Euler just with the vortex stretching and proved the blow up. I think personally prior to this work I thought that this kind of thing was a little bit it didn't seem to be on firm foundation, but it turns out that it's precisely what led to this kind of things. Second inspiration was a work of Kiselev and Schwerak. So in this work they explained how you can, in certain scenarios, so they had a very particular scenario where you can decompose the Biot-Savart law in 2 dimensions into a main part which was much larger than a second part. Okay, so let me explain this second thing. So this is second ingredient is a decomposition of the Biot-Savart law. Or okay, another way is it's just a decomposition of these kind of operators, so singular integral operators. Okay, and here again I'm going to start with just an example. Okay, so first it's well known that these singular integral operators are bounded on C alpha, but there's a problem when alpha goes to 0. So it's well known that the operator norms, so even for general elliptic operators, you have some problem with sending alpha to 0. So the operator norm is bounded like a constant divided by alpha. Okay. So now we want to understand how to characterize this failure. So can we characterize this 1 over alpha? Okay. Okay, and this you can just consider the following examples. Okay, so this is actually taken from Professor Lin's book on elliptic PDE. So you just look at the following function. Okay, so it's in 2 dimensions. So let's take psi to be this, and it doesn't matter to localize it or not localize it. Okay, so you can think of this and multiply it by e to the minus x squared, whatever, it doesn't matter. Okay, and now let's compute the Laplacian of psi. So Laplacian of psi, because x1, x2 is harmonic, right? The derivatives, at least one derivative must hit this one, which will pull an alpha down. Right? So what you see from here is that the C alpha norm of the Laplacian is of order 1 over alpha. Okay? But, sorry, is of order 1. C alpha norm of Laplacian is of order 1. But if you take a mixed derivative of psi, right, then you can just hit these 2 and you get 1 over alpha. And it turns out that this is basically the only example of where this can happen. Okay, so what's the theorem? So you see that there's only 2 harmonic polynomials of order 2, right? So once you get rid of those, this basically cannot happen. So let me explain what I'm saying. So this is a theorem. So let S greater than or equal to 0. And let's say that F is in HS. Let's see. Capital F is in HS from 0 to infinity across S1. Okay, so this I'm thinking about polar coordinates now. Okay, so F is a function of two variables. One is the radial variable, and one is the angular variable. And assume that for all r, f of r inner product with e to the 2I theta on S1 is 0. Okay, so this is basically the functions x1, x2 over x squared, and x1 squared minus x2 squared over x squared. So these are so basically I'm saying you cannot have that. So suppose that your function does not have this Fourier mode in theta. Then let's compute the second derivative of the inverse Laplacian of capital F. Okay, so this doesn't matter at all, but it's just good to write it like this. So if you compute the second derivative of the inverse Laplacian of a function of r to the alpha, so f now is an L2 function or a very smooth function of r to the alpha and theta, you assume that that mode is gone, then this, first of all, is a function of just r to the alpha and theta. So that's the first statement. And second of all, g in HS is bounded by a constant f in HS. And the constant is independent of alpha. Right? So this is independent of alpha. Okay. As a corollary to this statement, a corollary is that if you remove this condition, then the lack of uniform bounds as alpha goes to 0 is only going to appear in one term. So this means that you can write this as g1 plus g2, and g2 is uniformly bounded by f, independent of alpha, and g1 is basically, it's a radial function depending only on the integral from r to infinity, integral from 0 to 2 pi, omega of s and theta over s, e to the 2I theta d theta. Okay, so the only singular part of the singular integral is coming from this function. It's a radial function, and it only depends on this mode. Okay, and that's what we saw here. We saw when you take d1, d2, there's only one bad guy, and it's radial, and it's only coming from this one. Okay. Okay, so what does that mean? So the proof of this is it's not super complicated. So basically, just you change coordinates and you see something funny happens when in a certain mode in theta. So let me not go too far into it. But what it tells you on the Biot-Savart law, so I haven't made any symmetry assumptions on omega yet, on the vorticity. So what it tells you is that if you're looking at functions, so the natural class for us are smooth functions of these variables. So in 3 dimensions, you have to include the third variable. And so in any dimension, once you're orthogonal to the second order, the quadratic harmonic polynomials, this kind of thing holds. So it's not about dimension. So what this tells you is that you can decompose the gradient of u into a radial part plus an order alpha part. So this radial part has 1 over alpha sitting in front of it, and this part is just order 1, okay, plus a lower order. Okay, if you further impose, so if you further impose symmetry on omega, which is a reflection symmetry. So let me impose it on u. So ui of so u1 of x1, x2, x3 is minus u1, x1, x2, x3. And u2 and u3 are even with respect to this thing. And you do the same thing with u2, and if you put the minus here, etc. So you impose some symmetry. Then gradient u, the radial part, radial and diagonal. Right? These things you just have to compute. Right? So if you look at the main part of the gradient of u, you get a radial guy, which is also a diagonal matrix. Okay? And you keep reducing. So
We're supposed to think finally of alpha being small, I guess.
yes,
And that's the role of your epsilon later on.
exactly. Yeah, so the question is we should think of alpha being small, and that's the role of epsilon. And that's correct. Okay, so you keep reducing, but at the end, the simplest case to do this on is axisymmetric without swirl. Okay. And when I realized that it should apply to this, I thought that I had proved nothing and that I had just been deluding myself. Because the common statement is that solutions to the axisymmetric Euler equation without swirl are globally regular. Right? And that is true, but not in C1 alpha. So for solutions belonging to C1 alpha, this is not a true statement. So it's for smooth solutions. It's true that axisymmetric solutions without swirl are global. But that's one thing. But also, all of this does not require axisymmetry without swirl. So the main parts, doing it here is just to simplify everything, because then the vorticity becomes a scalar. So the problem becomes, so if I can just caricature a little bit. So if you go to axisymmetric without swirl, you get this okay, so it's not exactly as I'm writing it, but I'm going to just to make things easy. Okay, and you're solving this solved on x1 greater than or equal to 0 and x2 and on. Okay, so what this means is that you take the z-axis and you assume solutions are axisymmetric. Okay, so what it means is that U of OX is O of UX for every rotation matrix fixing the z-axis. Okay, so that's what the axis symmetry condition is, and you get an equation which is essentially this equation. Okay, so it's a two-dimensional problem now, right? And now with this information, we basically then, so this U is again given by this. So using, so first you change coordinates. You should change to like radial and angular coordinates. But once you do that, you see that a simple equation comes out. The only terms with 1 over alpha in front of them are the following. I should say on the domain, this is the Dirichlet inverse Laplacian. Okay. Okay, so now you do the alpha reduction. Using this statement, and you get the following. You get dt of omega. So maybe after you change variables, you should call it capital omega, plus some, put capital R to mean like the part coming from the radial part, plus some nonlinearity in omega. Okay, so now I have 1 over alpha in front of the main terms instead of yeah.
How do you get alpha to the equation? The ansatz inverse part of the alpha?
Yes, so the ansatz should be, you write omega of x1, x2 as capital omega of r to the alpha and theta, so little r, right? So this is capital R to the alpha is capital R. Little r is the x1 squared plus x2 squared to the 1/2. And that the correct ansatz for u is that u is little r times another function, capital U, of r to the alpha and theta. So you have to think a little bit about this, but that's the correct way to do it. Then you get an equation purely in capital R and theta. Okay, and now we're here. So the stuff I talked about in the beginning should convince you that we can just drop this n of omega part, as long as we can prove a stable blow-up for this one. Okay. And now I'm going to try to convince you that you can also drop this term. Okay. And this, it's not obvious from the these coefficients, but essentially, first of all, when you do the change of variables, a dr, a normal, if a derivative hits this, then you're going to get an alpha in the front. Okay, so anytime you take a radial derivative, you already have an extra alpha in this gradient. Okay, so that's fine. So the only problem is the angular part. So let's say this is the angular part. Okay, and then now it's about what space you use. Okay, so let me just give a small intuition. So this is what we learned from studying one-dimensional equations. So some small intuition as to why you can forget about that term. So let's consider this type of equation. Okay. So we're going to look at data like that, and we're considering dxxu minus dxxu to be omega. Okay. Okay. Then, okay, if omega 0 looks like this, then dxu is going to be positive here. So u, because u is the inverse Laplacian of omega, or minus, u is going to look something like that. So that's how u looks if this is how omega looks. Okay. That means that this term is pushing out like that. So the velocity is pushing you like this. But at the same time, you have the stretching from dxu. Right? So this trying to push you up. Okay. Now, if you have a linear type of 0 here, then the two exactly balance. Right? If you compute what ddt of dx omega at 0 is, you get that it's 0. If you just plug it in. So the regularizing effect coming from this term and the growth effect coming from this term exactly balance when you have a linear function. But if you have a function which looks like this, okay, so now it's talking about C alpha in the angle, not only in R. Then this term will dominate. Okay, so the pushing of this term is not strong enough to stop the growth. And you have actually blow up for this in C alpha and global regularity in C1. So that's a very interesting fact. So here, essentially what I'm saying is that you have to take advantage of being just C alpha in the angle as well. And this is actually the main use of the C alpha. Okay, there are several uses of it, I have to be honest, but the one which is, I think, deadly in the direction of getting smooth solutions is this use. Okay. Okay, so if you agree with my hand waving, then you can forget about that term. And you come to the fundamental model. And
I hadn't understood. So being only C alpha for small alpha means this term can be more singular than you otherwise would have expected.
this term,
Yeah.
less singular. Because it's, okay, at the end of the day, it's like this. If you have theta times d theta of a function of theta to the alpha, you get it becomes like alpha theta to the alpha. That's the idea. So this u is vanishing at theta equals 0. It's vanishing. The main issue is on the axis. So this is vanishing at the point where omega would only be C alpha. So that will give you another smallness. Okay, so this can be built in the spaces which you're using. So if you use the right weighted space now in the angle, you can see that this is a lower order term. But there's a lot of work that goes into that. So in the end, you end up at what I called the fundamental model. I didn't define what L12 is, but I'll do it now. So you arrive at this model. So you forget about the 1 over alpha. Just scale it. And L12 of omega is just the integral. Okay, now it's a radial function. So we said that the gradient of u is just going to give you radial contribution. Okay, now in this geometry it's like that. Omega of s and theta, sine of 2 theta over s ds d theta. Okay, so the dependence is only in this. So L12 is maximum. So you're thinking that capital omega is 0 at 0. So it looks something like that. So now we're thinking now about smooth solutions. So this is after all of the change of variables. So you think that capital omega looks like this. Then L12 of omega is going to be maximal at 0, look like that. Okay, so it's not surprising that multiplying this by this causes the maximum to get closer to 0, and that only strengthens this guy in the middle, and you have a blow-up. And you can, in fact, write down an exact self-similar blow-up for this. And the reason is that this is only a function of r. This is a function of theta. So you can, you have a nice property of this equation that if omega 0 of r and theta is just a function of r times another function of theta, then the solution will only change basically in r. The theta part does not change because you're only multiplying by a function of r. Okay, so you can basically solve this problem. And that's the construction. So I think I went over time. So thanks.
So basically, capital R theta is of little r and the z, right?
Correct.
Right.
Correct.
So if it's not compact support, you have three really rotating everywhere. This
Yeah.
way, and then you little shoot up.
Exactly. So that it's going, it's coming like this. So it's rotating like that, and it's going out. So if you want a blow up for smooth solutions, you should really have it the other way. But
The stability argument from again. Can you say this a bit?
so, right. So other.
Because this solution is constructed this way, the semi-similar one is decaying at infinity but not too strong.
Correct. Yeah.
And
So
even the one with interest constant here or whatever argument you use will also not that strong decay.
correct. So this self-similar solution will decay like 1 over the original r, 1 over the real. Okay, so let's just say x to the alpha, right? So this is the kind of decay at infinity you're going to get for the profile. So how you construct the solution. So if I can come back to this issue. So in the very beginning we talked about L of G is a bunch of stuff, right? And I told you how you get like sort of an a priori estimate on G. Okay, but to actually construct the solution, you add this tau variable and solve this equation.
You're going to similarity variables.
Now you're going to similarity variables, right?
So you need to somehow show that this solution you constructed is stable enough that you can run until.
Yeah. So the coercivity of L gives you that this problem will converge to a stationary state. But it also gives you that if you added any forcing, which may come from a cutoff or subtracting something, it will also converge to a locally self-similar. So you just have to go to similarity variables and again use this. The whole thing is the coercivity of this. The stability and the construction are based on the coercivity. So you didn't need to start at 0 either, right? And another thing is that the space, right? So the space in which where we allow perturbations allows for decay like this. So allows for even slower decay, right? So if you subtract the right perturbation, you can exactly kill the original one. Okay.
Is this solution energy will be finite?
Yeah.
What is it? Is in the under you got the complex form.
Yes.
Without the perturbation, you will have the form.
Correct. Without the perturbation, you have infinite energy. Yeah. Yeah. Yes.
Do you have a guess as to what's the separation between blow up and positiveness for the?
Okay. So in this case, I strongly believe it's alpha equal 1/3. Right. So it's nothing to do with the Onsager 1/3. So. Okay, so if you write down so let me write down one thing. So it's like I said, the first alpha I don't believe is I think is just a technical thing which allows us to do it. The alpha in the angle is the real bad guy towards getting the smooth thing. So the equation one should consider is the following. So it's I should also say that the classical theorems break down at 1/3 also. So the classical global regularity theorems break down exactly at 1/3, and you can see it from this equation. Okay, so you say this is the reduced model you get before dropping the transport term. And you say you have 3/2 sine of 2 theta d theta. And they have the same coefficient. So it's like 3 u dx omega is u dx is omega dxu. It's like that. This is the kind of equation we're talking about. 3u dx omega is omega dxu. And the balance in that argument I was talking about in 1D is exactly for things of 1/3. Right, so when you have a 1 here, the balance is at a linear function. If you increase the power of this, the balance is at 1/3. And it's interesting that the classical theorems also got that. But I guess without knowing this stuff, I don't know.
Okay.
Okay.
Thank you so much, Tarek.
Thank you.